The National Academy of Engineering, the European Academy, a member of the American Academy of Arts and Sciences, president of the International Federation of Computational Logic, honorary doctor of several European and American universities. He is included in the list of highly cited scientists of the Institute of Scientific Information. He is winner of 3 IBM Outstanding Innovation Awards, the Goethe Prize for his work in time logic with Spanish Automata, and many other prestigious awards. He was awarded the Blaise Pascal Medal in Computational Science by the European Academy of Science. We hope that in the future, the favorable times will come and Professor Vardi will be able to visit our Kazan University, while we are making far-reaching plans for online cooperation with Professor Vardi with our scientific and educational mathematical center. Professor Vardi, you are welcome for your talk.
Thank you all. Thank you for the very kind introduction, and good evening to you. So today I would like to talk about a logical revolution. And I will start with the first slide in something giving you a summary of the story. And it's a story how in the past 50 years, there has been extensive, continuous, and growing interaction between logic and computer science. In many respects, logic provides computer science with both a unifying foundational framework and a tool for modeling computational systems. In fact, logic has been called the calculus of computer science. The argument is that logic plays a fundamental role in computer science, similar to that played by calculus in the physical sciences and traditional engineering disciplines. Indeed, logic plays an important role in areas of computer science as disparate as machine architecture, computer-aided design, programming languages, databases, artificial intelligence, algorithm, and computability and complexity. And what I try to do today is in 1 hour is to try to tell the story of how that happened. But first, how did this connection between logic and computer science even happen? If you go and you ask people what is logic, they would say, oh, it's part of philosophy. Maybe they know about Aristotle. But computer science is still on campus the youngest intellectual discipline. How did the two get connected? Martin Davis, very senior, very distinguished logician, I'll come back to him later in the talk, wrote an article in 1988, so already quite some years ago. He said, when I was a student, all logists regarded mathematical logicians as living in outer space. Today, the connection with logic and computer are a matter of engineering practice at every level of computing organization. And the question is, why? How did it happen? How did this connection happen? So for this, we have to go back to the 19th century, where people start thinking about what's called philosophy of science. Try to understand, okay, science has been enormously successful. What is the scientific method? Okay, so these people start thinking about the meta theory of science. And today we understand what is the scientific method. Especially in the physical science, it's very clear. We construct a mathematical model of reality, like Maxwell equation, Schrödinger's equation. And then we analyze that model. We make prediction about what should happen in the real world. We run experiments when we compare what the theory tells us versus the experiment. But this raises another question. What is a mathematical model? We use the phrase, but it's a vague phrase. And in 1879, a German mathematician, Friedrich Ludwig Gottlob Frege, asked even a more fundamental question. What is the language of mathematics, he asked. And he wrote a small book called Begriffsschrift, which is a language for concept, in which introduced, he argued, is the universal mathematical language, which today we call first-order logic. And this is part of a philosophical movement called logicism to base mathematics on logic. And what is this universal mathematical language? You have objects, you have predicates, relationship between them, 2 is less than 3. You have operations, 2 plus 3. You have Boolean operation. Okay, this is Boole wrote his book in 1849, so about 30 years prior to that. And then with Boolean operation, and then later after bool, the quantifier we introduce by Peano and Peirce. For all there exists, we use inverted A, inverted E, and so together, all these things together give us first order logic. So you can go back to the Aristotelian syllogism. If you say all men are mortal, then you say for all x, if x is a man, then x is mortal. And we write it in our syntax now, for all x, inverted A is for all x, man of x, mean x is a man, arrow implies x is mortal of x. And once we have this language, we can go back to the question, what is a mathematical model? And that was introduced by Tarski, and he looked at a whole bunch of mathematical structure, graphs, partial order groups, string, fields, many structures. And Tarski said they all have the same format. They all have the same basic syntax. We have a domain, the universe. It's a non-empty set of objects that we are talking about. We have relations over this domain, Emery relations, and we have n-ary functions. So he said the combination of domain, universe, relation, function, that is a mathematical model. So now first order logic is able to talk about mathematical models. Let's take example. If we have a graph, then the universe is a set of nodes, and we have one binary relation, which are the edges. This is directed graph. And then I can say something like for all x there exists y, such as u of x, y, and this says that the graph has no sink. Every node has an outgoing edge. Or a group, again, is a universe, is a set of elements, and we have one binary operation, the product operation. And we can say, for example, the group is commutative by saying for all x, for all y, x times y equal y times x. So now we have a universal language for mathematics. I'll use as running example, I'll use graphs. So in graphs, we have the first order variable, which runs over nodes. We have atomic formulas. U of x, y said there is an edge from x to y, and x equal y said x and y are identical. And from this, we can form more complicated sentences. We have atomic formulas with Boolean connective, first order quantifier. We can form now more complex sentences. So let's see an example. I can say the node x has at least two distinct neighbors. Then I will say there exist x, y, and z such that not y equals z, so they are distinct. And there are edges e of xy and e of xz, say there is an edge from x to y and an edge from x to z. So every node, so the node x has two distinct neighbors. Now the node x here is free. I don't tell you what is x. So in order to say whether this is true in a graph, we have to provide binding. We have to bind free variables to elements of the graph. So it's the semantics, which we denote by double ternstile. G satisfies relative to binding alpha, the formula phi of x. Now I can say each node has at least two distinct neighbors. Now I'll quantify over x universally for all there exists y and z, Now it has no free variable. It's a property of graphs. It describes a property of graph. Every node has at least two distinct neighbors. Now, this is an important distinction between formulas and sentences, and I'll come back to it in a sequel. Now, if this was the first book was published in 1879. In 1903, another volume by Frege is about to come out. And now we have a letter from Bertrand Russell to Frege, and Russell agrees with Frege. He said, I find myself in agreement with you in all essential. I find in your work discussion, distinction, definition that one seeks in vain in the work of other logicians. There's just one point where I've encountered a difficulty. And this difficulty was so severe that in 1903, in the appendix to Frege's to the book, Frege writes, there's nothing worse that can happen to a scientist than to have the foundation collapse just as work is finished. I've been placed in this position by a letter of Bertrand Russell. So Russell found a major contradiction in Frege's work. And ultimately that led to the so-called Hilbert's program. And the program was to formalize mathematics. And Hilbert had three goals. One is to show that mathematics is consistent. you cannot prove a statement and its negation. Mathematics is complete. All true mathematical statements can be proved. And finally, mathematics is decidable, which is there is a mechanical way to determine the truth of a given mathematical statement. So these were the three legs of Hilbert's program: consistency, completeness, decidability. Now, so the Hilbert program was launched after World War I in the 1920s, but by the 1930s the program was brought to demise, first by Gödel, who proved incompleteness. You cannot systematically derive all mathematical theorems. You cannot prove the consistency of mathematics. This is the first and the second incompleteness theorem. And Gödel, of course, used the famous what we call the Gödelian sentence that says this sentence is not provable. And of course, if you prove it, then you have a contradiction. So incompleteness and we have the two gaps, right? Inconsistency, incompleteness, and the final one, undecidability, was shown independently by Church and Turing in the mid-30s. The set of valid first-order sentences is not computable. And the question, in fact, the way this happened is that in the book by Hilbert and Ackermann in 1928, they posed the so-called Entscheidungsproblem, the decision problem. Given a first-order sentence, decide if it is valid or dually satisfiable, and Church and Turing both proved independently that this problem is unsolvable. And one thing that came out of it is that Turing defined Turing machine to define decidability. We had to define what does it mean to be decidable. So he defined Turing machine. He showed the termination problem for Turing machine is unsolvable. And then he showed that this can be reduced to the decision problem. So now we are in, let's imagine where we are with logic as foundation for mathematics in the mid-1930s. Remember that logicism was to try to base logic as foundation for mathematics. But by mid-30s, we know that we have incompleteness. For example, not only the Gödelian sentence, but basic mathematical statements such as continuum hypothesis, we cannot prove them. Mathematics cannot prove its own consistency. The decision problem is unsolvable. So logic is foundation of mathematics. It's a big disappointment. What can we do with it? And people say, okay, can we get some positive result? We have lots of negative results. Can we get some positive results? And one way to do that is to focus on fragment of first-order logic. And one way to define fragment is to focus on the quantifiers. So we have classes that are defined by quantifier. Schenfinkel class has exist star A star. It means first you start with a string of existential quantifier followed by a string of universal quantifiers. And this class is decidable. This class has, you go from existential to universal. Can you alternate? So Ackermann showed that you can have exist stars, A exist star, one universal quantifier. If you have only one, it's decidable. If you have two, this together class, it's undecidable if you have equality. So, and these are only three classes. We have Bernet, Schenfinkel, Ackermann, Gödel class without equality that are decidable, but they are very weak classes. So what good is first order logic? These are very weak classes. So another attempt is to say, okay, let's not focus on the syntax, let's focus on the domain we're interested in. So how about integer addition? So here we have the natural numbers as universe, the domain. We have binary predicates and we have addition operation. And this is enough to express, if I want to say y equal multiplication by constant, y equal 2x, it's just like y equal x plus x. I can express that x equals 0 to x equal 1. I can express successor. So it's actually a fairly expressive theory. It can express a lot of stuff about what we call linear arithmetics. We can do integer programming, integer inequality, and so on and so forth. In 1929, Moshe Pressburger, a Polish mathematician, proved that this linear arithmetics is decidable. And he did it first by proving sound and complete axiomatization. and then even a decision procedure. He used quantifier elimination. Today we're using automata, but the point is it's a fairly expressive theory and it is decidable. However, there is a problem. Decidability itself is not good enough. So people have investigated what is the complexity of Pressburger arithmetics, and we see that this has been investigated in the 70s. And on one hand, we have triply exponential bound, upper bound, and then we have a double exponential lower bound. And in fact, Michael Rabin, a very distinguished computer scientist, felt that how can you have AI if you don't even have linear arithmetics? And he wrote a paper in 74, Theoretical Impediments to Artificial Intelligence, and he wrote the complexity result point to a need for more careful examination of the goals and methods in AI, because to him, he thought that linear arithmetics is a very, very foundation of any kind of automated reasoning. Another class that we can discuss, which is less than all of first order logic, is first order logic is monadic predicates. All the predicates are monadic, just one place predicate. So for example, we can say if for all x p of x and for all x p of x implies q of x, then it follows that for all x q of x. So it turns out that all the Aristotelian syllogism can be expressed in monadic logic. So good question, is this class decidable? And Lovenheim showed in 1915, yes, this class is decidable. Okay, so monadic logic is decidable, and this goes back to Lovenheim 1915. How do you prove decidability here? So there are different ways to do that. The point is that one way to do this is to look at deterministic finite automata. So this is a special computational model. It's a Turing machine, but without the tape. Instead, we have a finite alphabet, a finite set of states, initial states, a transition function, given a state and letter, it goes to the next state, set of accepting state. And here is a little picture. We have two states. You enter on the left, 0 always takes you to the left, 1 takes you to the right. The red circle denote accepting states. These are deterministic finite automata, and then define the class of all regular languages. So this is a very robust notion. The class of regular languages, they can be defined using deterministic finite automata. So this model was hinted by Turing in 1950, and then logicians start studying it in the middle of the 1950s. Now, you can also look at finite words as a mathematical structure. Remember, what is a mathematical structure? It's a universe, it's a domain, a predicate. Here we have one binary predicate that tells us which position comes before which position. And the monadic predicate tells us what letter is written in what position. P sub A is true at position in a given position if the letter A is written in that position. And now we can look at what monadic second order logic, in which we have the atomic formula, the monadic atomic formula, the dyadic formulas x less than y, but also we can quantify not only over elements, but also over sets of elements. And that seems to be important. I will see in a minute why. But here is a simple sentence. It says there exists x such that for all y is not larger than x. So this tells us x is the maximal element. So it's the rightmost position in the word. And p sub 1 of x. That means the last position in the word is 1. So we can describe properties of words, and we can define languages, which are set of words. Turns out you can also define, this automaton that we saw before is how does the DFA accept? The DFA accept if you have a sequence, which is a sequence of states where you start with the initial state and then you follow the transition function, and the last state has to be accepting. And so here is an automaton that starts on the left, 0 takes you to the left, 1 takes you to the right. You must end up with 1. And the same thing you have with logic. So you see we can define the same language with automata or logic, and that's not a coincidence. That was shown by Bushy and Elgot in the United States, and Trachtenbrot, I think at the time he was in Novosibirsk, and all three of them prove independently that monadic second order logic has the same expressive power as the deterministic finite automata, that define the class of regular languages. And the translation is effective. You can go from DFA to MSO, and you can go from MSO to DFA. You can go in both directions. So this is an amazing connection between a computational model and a logical model. Now, it's also useful from a practical point of view. Why is that? So the most fundamental decision problem for automata is, given an automaton, is it non-empty? Does it accept any language, some word, does it accept some words? And that's called the non-emptiness problem. Decide if A is non-empty. And it turned out to be algorithmically a very simple problem. You can look at the graph, at the directed graph that underlies the DFA, where the nodes are the states, and you have an edge from S to T if you go from S to T when you reach some letter A. And an easy undergraduate level lemma is to prove that A is non-empty if and only if there is a path in this graph from the initial state to some accepting states. And because this is just graph reachability, it can be done in linear time in the size of the graph using breadth first search or depth first search. So easy decision problem. Now another problem is, the analogous problem for logic is the satisfiability problem. Given a sentence, does it have a model? Is a set of models non-empty? And that seemed on the face of it to be a difficult question. You have quantifier, first order quantifier, second order quantifier. How do we decide if the language is non-empty? Well, we know that you can translate a sentence phi to an automaton A sub phi, which describes the same language. So clearly phi is satisfiable if and only if A sub phi is non-empty. So the algorithm is very simple. Translate psi to the automaton and check non-emptiness of the automaton. We know that the second step can be done in linear time in the size of the automaton. So the question is, how big is this automaton? Well, if you just analyze the translation, you find out the translation is very, very costly. The naive upper bound is what we call non-elementary growth, which is 2 to the 2 to the 2 to the 2 to the n, where the height of the tower is linear. So this is the naive algorithm, but Stockmeyer has shown in 74 you cannot do better than that. In fact, even first order logic is already non-elementary. There's no bounded height tower. And this grows incredibly fast. 2 to the 2 is 4, easy. 2 to the 3 is 2 to the 8, 256. 2 to the 2 to the 2 to the 4, I computed it for you, and it's about 4 billion. But 2 to the 2 to the 2 to the 2 to the 5, I cannot compute it precisely already because it's a number in the scale of 10 to the billion. So it's already a humongous number. We cannot compute it effectively. So there is a question whether if you have such non-elementary bound, what can you do with it in practice? It's decidable, but is it practical? But it turns out that computational complexity is problematic even in the very foundation of logic. So in 1849, Boole published a book, you'll see the book in a minute, in which he takes the Aristotelian syllogism and treats them algebraically. So the 19th century were the century of the explosion, all kind of abstract algebras, groups, rings, fields, and Boole introduced Boolean algebra. And his main argument is that logical conjunction can be viewed as a multiplication operation. And logical disjunction can be viewed as an addition operation. And on top of it, we also have negation, so we have 3 operations, and this gives rise to Boolean algebras. And here you see a picture of me in 2017. I visited University College Cork in Ireland, and they asked me if I'd like to see their collection of Boole's book. I said, sure. And so they take me there and they say, would you like to hold Boole's personal copy of his own book? And so here you see me holding Boole's personal copy of his own book. I was so excited, my hands were trembling. And after that, for a week, I didn't wash my hands because they touched such an important document. Boole's own copy of his own book. Now, Boolean logic gives rise to an important decision problem, Boolean satisfiability. Boolean satisfiability, we're given an expression using and, or, and not. And we ask, can you assign Boolean values, 0s and 1s, So the whole thing would be equal, the whole expression would evaluate to 1. So here is an instance. I have a conjunction of the junction of positive or negative variables. And it's easy to see that if I make x1 and x2 0 and x3 and x4 1, then the whole thing evaluates to 1. Now here it wasn't so bad. There are 4 variables, so there are 2 to the 4. There are 16 possible truth assignments. But what happens if instead we have 40 variables? Okay, maybe you can do that by brute force. What if we have 400 variables or 4,000 variables? How can we solve Boolean satisfiability problem? And already in the 19th century, people realized this is a difficult problem. And William Stanley Gibbons, who was a follower of Boole, wrote, "I've given much attention, therefore, to lessening both the manual and the mental labor of the process of Boolean reasoning. And I shall describe several devices which may be adopted for saving trouble and risk of mistake." He actually built logic machines that can do reasoning. His machine could reason about four variables. A bit later, Ernest Schroeder, a German algebraist, wrote, "Getting a handle on the consequences of any premises, or at least a faceted method for obtaining these consequences, seems to me to be one of the noblest, if not the ultimate goal of mathematics and logic." And because people saw the only way they could see how to do that was using exhaustive search. And that led this realizing that many problems seems to be only amenable to exhaustive search gave rise to a research program in the Soviet Union in the 50s and the 60s, the so-called the Peribor program, that tried to either show that you can do better or show that you cannot do better exhaustive search. Well, as you know, the problem is still open, but in 1971, Cook and then independently Leonid Levin in the Soviet Union proved the Boolean satisfiability is NP complete. So this would give us, at least told us that many problems that seem to require exhaustive search, it tells us they are equivalent problem. You solve one efficiently, you solve all of them efficiently. You show that one is hard, you show that all of them are hard. And this is the class NP. These are the class of problem where solution can be checked in polynomial time. What does it mean to check? Let's suppose I want to know if a number is composite. Well, give me the factorization and I can multiply them and check if they give me the number. Okay, so this is clear in NP. Hamiltonian cycle, give me a candidate path, and I can check easily if it's a Hamiltonian cycle. And it turns out that there are tens of thousands of problems that are in NP, because if you have somebody give you a solution, you can check it easily. NP complete means the hardest problem in NP in a formal sense. So if one NP complete problem is in NP is in polynomial time, then all of them are in polynomial time because they're all interreducible to each other. Now, is it possible that P equal NP? Well, the answer is mathematically yes. People think it's very unlikely. It is what a theoretician from MIT wrote some years ago. He said, if P equal NP, then the world will be a profoundly different place than we usually assume it to be. There will be no special value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once it is found. Everyone who could appreciate symphony would be Mozart. Everyone who could follow a step-by-step argument would be Gauss. So the common belief is that Boolean satisfiability cannot be solved in polynomial time. It's a hard problem. This is the common belief. Now, again, talking about logic in computer science, there was another attempt to use logic was to prove the correctness of programs. And this dream was laid out by Tony Hoare in 1969. And he proposed mathematical axiomatization of correctness. And he wrote, when the correctness of a program, its compiler, and the hardware of the computer have all been established with a mathematical certainty, it will be possible to place great reliance on the results of the program. So that was the program verification dream. Even though people argue against it, 1979, DeMillo, Lipton, and Perley said they were very skeptical that this can happen. And the argument was that at the end of the day, the acceptance of mathematical proof is a social process. Take Fermat-La theorem. I believe that the theorem is correct. It was proven by Andrew Weil in the early 90s. Did I read the proof? No, I did not read the proof. I just trust the people who did read the proof and say, yes, we believe this proof. So it's a social process. The argument was that by DeMillo et al. Was that the proof for computer programs are going to be so long and so uninteresting, nobody will read them, and therefore there will be no trust, no social process. This is debatable, but this was the argument they made, and it was a powerful argument they made in 1979. So let's look at where logic was in computer science in around 1980. And 1980 was a very, very special year for logic in computer science, because that's when I started my PhD. This is a joke. So here is what I saw. The termination problem is unsolvable. First order logic is undecidable. The decidable fragments are too weak or too intractable. Boolean logic is NP-complete, intractable. Program verification, hopeless. So again, even if you take you don't try to lay foundation for all of mathematics, but just for computer science, again, it seems somewhat hopeless. But that situation has changed after 1980. And there have been progress on many areas, in databases, Boolean reasoning. I'll explain what is model checking, termination checking. Logic went from irrelevance to relevance. And that's the story of the second half of the talk. So remember, we made a distinction between formulas that have free variable and sentences. Sentences describe properties of structures. For example, a sentence psi is just true or false on a given graph. So you can define the class of graph called models of psi, which are all the graph that satisfy psi. G double tensile psi means G satisfies psi. So logic gives us a way to describe classes of structures. So logic is the meta language for mathematical modeling. And it gives rise to a branch of mathematical logic called model theory. Okay, mathematical logic is divided into model theory and proof theory and set theory and computability theory. These are the legs, and model theory is one of them. And for logicians, really formulas are just less interesting. They are just a way to build sentences. Sentences are interesting because they describe properties of structures. But in 1970, Ted Code, at the time at IBM Research, argued that formulas define queries. So he said, suppose you're given a formula phi with x1 to xk free variables and a graph G. So remember, to decide if the graph satisfies phi, you have to provide some binding alpha, such that to bound all the free variables. And Ted Code says, well, the set of binding that satisfy the formula, this is an answer to a query. So if we go back to the sentence that says x has two distinct neighbors, and x is free here, Ted Code says, think of it as a query. Give me all the nodes that have at least two distinct neighbors. So now we have a declarative query language, first order logic. And people started after his paper published in 1970, people says, wow, it is going to work in practice. And it took about a decade to show that this would work in practice. And by ultimately, we have today a query language. SQL is based on first order logic. And ultimately, Ted Code received the Turing Award in 1981. And Mike Stonebraker, who one of the first implementers of relational databases at Berkeley, received the Turing Award in 2014. And today, relational databases are tens of billions of dollars. It's a large industry. And a friend of mine says that Western civilization is based on relational databases. If suddenly somebody, a magician, waves a wand and all relational databases fail, then suddenly we'll have a societal collapse. So what were Ted Code actually has two fundamental ideas in that paper. One is a connection between mathematical relations and table. This was just an observation that looks trivial once you see it. He said, look, what is a table? It's a set of rows. Okay, because the order of the rows doesn't really matter. The order of the column does, but the order of the rows doesn't matter. And what is a relation? It's a set of tuples, and rows and tuples are the same. So a mathematical table is just a relation. And it said formulas are query, as I explained, they are declarative queries. And so now we have a way, a universal data structure to store information. So we said mathematical structure can be used as databases, and Further logic can be used as query language. And as I mentioned, it was reduced to practice first by IBM in System R, same year Ingress at Berkeley, and then commercial product Oracle and DB2, and that led to Turing Award in a decade, which is in less than a decade, in about a decade, 11 years, which is very fast. Now remember that I said before something about first-order logic being undecidable. So how can we build commercial system based on undecidable problem? So here we have to distinguish between the satisfiability problem, given the first-order formula, is there a graph and binding that would satisfy the formula psi? And the truth evaluation problem, given a first-order formula and a final graph G and binding alpha, does G satisfy phi relative to alpha? The first one is undecidable. This is from Church and Turing. The second one is actually obvious. It's decidable because all the quantifiers range over a finite domain. So you just have to try. Whenever you see for all, create a loop. Try all of them. Whenever you see there exist, again, create a loop and find one. So this is clearly decidable. So this was, again, it's an obvious observation, but very important observation by code. The truth evaluation, which is what we need for query evaluation, is decidable over finite graphs. Now let's go back to the satisfiability Boolean reasoning, which we saw is incomplete, so seems to be intractable. Well, people nevertheless have tried to build programs to do Boolean reasoning very early on. Remember, one of the first computers was the programmable computer was the ENIAC. Was turned on in 1946. Less than a decade later, Newell, Shaw, and Simon write a program called the Logic Theories for Boolean reasoning. 1958, Davis and Putnam published a technical report to the National Security Agency about computational methods in the propositional calculus. It was classified then, today you can find it. Then Davis and Putnam published a paper in 1960. Davis, Logman, and Loveland published another paper in 1962 that gave rise to what we call today the DPLL method. You convert the formula to conjunctive normal form. What we saw before was a conjunction of disjunctions. You just run a backtracking search, just per abor, and there was one heuristic that if we saw before, let's go back. Yeah, here, if one of the clauses, one of the disjunction only has a single literal, positive or negative. Suppose the first one just said not x1, that there's no need to branch. We know that x1, because it's a conjunction, we know that x1 must be false. So this is the so-called unit clause preference. Start always with unit clauses. But the method, when I was a PhD student, the people could solve problem with maybe hundreds of variables. And when you said them, but these problems are not of interest to industry, they said, well, it's an epic-complete problem. What do you expect us to do? Miracles? But something started happening in the mid-90s, and there was an explosion of new heuristics. And today, the new such solvers are called CDCL, conflict-driven closed learning. And there is a collection of heuristic here, starting from back jumping, which is when you backtrack, don't go one level at a time, jump many levels. How to do unit clause preference in a smart way so the overhead will be minimized. If you have an assignment that fails, learn from your failure. Don't repeat the same mistake. There must be a bad partial assignment that's bad, block it, and so on and so forth. Many heuristics. And important tools came out in the mid-90s, GRASP, 2001, SHAF. And today we solve problems with millions of variables, industrial problems with millions of variables. So about a decade ago, a colleague of mine decided to see how much does such solving progress over a decade. So he tried to see what happens over a decade. So he took a decade of such solver and benchmarked them on the same problem on the same machine. And he showed that in 2000, the state-of-the-art tool was taking 800 seconds. And by 2012, the state-of-the-art tool was taking 1 second. So this is 3 orders of magnitude improvement over a decade. And this improvement has continued. People talk about Moore's law for SAT solver because the progress has been so impressive. And today, SAT solving is industrial reality. There was a paper from 2012, Leonardo de Moura and Nicolas Bjorner, they describe application of SAT solving in software development in Microsoft. Software development, not in research, in actual development. There are many applications in software development. And as we speak now, there are hundreds of machines in Microsoft running SAT solvers for software development. It's an industrial reality today. So this has been amazing progress. Now let's go back to program verification. So in 1977, Amir Pnoeli argued that the focus of the Tony Hoarhead in 1969 on input-output relationships is not broad enough. He said there are many programs that don't have clear input and output. Protocols, hardware, operating system. It's all about ongoing interaction. He said we need to reason about ongoing interaction. And for that he proposed a logic that was borrowed from philosophy, linear temporal logic, which I'll show in a minute. Okay? And he said you can specify properties of non-terminating programs, and you can reduce it then to monadic second-order logic. And so it is decidable, but remember, monadic second-order logic is non-elementary. We saw this before. So what are examples of linear temporal logic? Here are some very simple examples. You can say always, not CS1 and CS2. So here CS1 and CS2 stand for critical section. This is mutual exclusion. You say you cannot have two different processes in a critical section at the same time. That's a safety property. This is how you specify it in linear temporal logic. You say always request implies eventually grant. If you make a request, eventually it will be granted. That's a liveness property. Or another liveness property, if you make a request, the request will stay on. The semaphore will stay on until it is granted. So this language has been made very popular and very successful. And then people have developed algorithmic approaches to verify temporal properties. So this is called model checking, because unlike Hoare verification, which is you just have to derive proof axiomatically, here you run an algorithm to check properties. The first two papers were by Clark and Emerson and Ken Sifakis in 81, 82, and they use a logic called CTL. But in 85, Pnoeli and Lichtenstein came back to linear temporal logic, and they show that you can use it, you can do it in time, which is linear in the size of the program. This is the state space of the program, which can be quite large, and exponential in the formula. And for this, they use a set of heuristics from philosophical logic called Tableau. And so now we have a somewhat strange. Tableau is a set of heuristics. On the other hand, automata, we saw them before, give us very elegant theory, but it seems to be non-elementary. So can we use automata while having the same complexity that we have here? And this was shown in the 80s by Pierre Wolper and myself. And we showed that you can take a formula LTL of size phi, and we can construct an automaton of exponential size. And so we have now automata of exponential size. And now we have automata theoretic algorithm for satisfiability and for model checking. And today we went from LTL to industrial languages. I won't get into detail what they are, but languages are called PSL and SVA. They're both IEEE standards. So we went today, we can use reasoning about temporal logic, and today it's being used in industry. And remember the issue of, again, of termination is undecidable. In 2011, Cook, Podelsky, and Rabalchenko showed that while termination is undecidable, but in practice is not always undecidable. And they built a tool called Terminator, which is actually can prove termination or divergence of many Microsoft programs. It's been actually quite successful. And this is somewhat surprising. How come we have decidability? And the answer is that most real-life programs, if they terminate for simple reasons. not for deep reasons, for simple reasons. Okay, if you have a program terminate, is not because of some deep theorem. And so, because programmers typically don't think about very deep things. So program terminate for simple reason, and therefore you can actually check it in practice. So logic went from failure to success. And how did it happen? Well, what do we learn from it? Algorithms are important, heuristics are important, running experiments is important, building tools and systems is important. And worst case complexity is maybe too pessimistic. We say it barks, but it doesn't bite. We have problems that seem to have terrible complexity, but in practice, they're not so bad. Now, my final observation would be that many people say today, who needs logic? We have machine learning. Machine learning, machine learning, machine learning, deep learning, deep learning, deep learning. So why do we need logic? So for this, I want to bring back a book that came up by Daniel Kahneman, a famous psychologist, received the Nobel Prize for economics. And the book was titled Thinking Fast and Slow. So he introduced fast thinking and slow thinking. Machine learning is fast thinking. You drive, you have like autonomous vehicle, you drive, and you have to recognize, is this a stop sign or not? And you have to do it in a second. What is logic? Logic is for slow thinking. What does it mean for slow thinking? When you see a stop sign, what should you do? Do you stop at a stop sign? That requires slow thinking. If you think about it from evolutionary point of view, you are in Africa, in the savannah in Africa, you see something yellow moving in the grass. Where you have to very quickly recognize this is a lion. This is fast thinking. You don't have time to decide. You have to get away out of there. Now you go back to your village and you want to plan a hunt for the lion. This is slow thinking. And the grand challenge today is to combine logic with machine learning. Very much.
Thank you very much, Professor Vardi. Thank you very much. And any questions?
Hello, do you hear me?
Yes, Stepan, I can hear you.
Yeah, thank you. So I just got unmuted. I couldn't do it by myself. They unmuted me. So I have the following questions. So all these, well, first, thank you for the talk and for this great survey of what happened in logic and how it's connected to computer science. The question is as follows. So all this, mostly maybe the systems you discussed in the talk, they are sort of have their roots in classical logic. So it's Boolean logic, and then its extensions to first order, second order systems and their fragments. What about non-classical systems? Could you comment a bit on that?
So, I mean, some says LTL is, if you look at what we call classical logic, then it will be first order logic is kind of classical logic. Now, temporal, if you look at the branches, in fact, temporal logic and modal logic, for many years, mathematical logicians kind of look down on this. So there are kind of two main journals in logic. There is JSL and JPL, Journal of Symbolic Logic, which was the mathematical logic. PL was Journal of Philosophical Logic. And if you look through the pages of JSL, you find there will be no mention of modal logic or temporal logic. Where would you find that? They say, oh, this is philosophy. You'll have to go to JPL to read papers about modal logic and temporal logic. This has changed now. And actually, it was partly changed by computer scientists. But computer scientists say, oh, for some applications, we actually need modal logic. I mentioned here temporal reasoning. And so Amir Pnoeli discovered that philosophers have been studying temporal logic. He said, okay, this is relevant to us. I wrote a book on reasoning about knowledge, which used epistemic logic. So computer scientists computer science were not driven by the language. They are driven by the problem they're trying to solve. So they would use whatever is appropriate, and that's how temporal and modal logic start receiving more respect from mathematical logicians. And today you can find papers on modal logic in the Journal of Symbolic Logic. But if you go back 30, 40 years ago, there was a very stark division. And today this division, I think, between classical and non-classical is kind of disappeared in some sense.
Okay, thank you. So at least model logic as an classical is okay. So maybe also intuitionism or some linear systems.
Today people use modal logic, temporal logic, epistemic logic. I mean, today these logics are used, and I'm saying they used to be second-class citizen in mathematical logic, but no longer.
Okay, thank you. That's a very good answer.
Radhakrishnan? Radhakrishnan? Okay. Dimitri?
Moshe, thank you very much for a very interesting lecture. Brett Mirzayevich, thank you very much for organizing this lecture. Yes, I have a question. You spoke about connection between machine learning and logic. And what do you think about semantic web, I mean, description logic, OWL, and so on? Is it perspective, perhaps, some ways to combine this approach? I mean, semantic web, description logic, OWL, and so on, with machine learning. And perhaps it's one of the way of new progress, new achievements in artificial intelligence. What do you think about this?
So, I mean, you can almost think like if you look at the web, look at the so-called the page algorithm, which was the first algorithm was used by Larry Page to rank the result of a web search, and by analyzing the links. And you can say, in some sense, this was some form of machine learning. And today, in fact, most of the way today that internet companies like Google rank the search result is by massive amount of machine learning to look at user behavior, who clicks on what. So clearly, machine learning is involved. There have been arguments now for many years is that the web is just a graph, and that's too impoverished model, not enough semantics there. Why don't we just try to get more semantics? And they were based the semantic web, and people said, well, we have a logic, description logic. Lots of research, I have not seen it having practical impact. So I'm just so far, all this argument that we must have more semantics in the web, I'm not convinced that this is a problem. If you look at one of our problems today on the web, is just deciding very simple question: what is true? What is a fact and what is misinformation? What is disinformation? We're all struggling. You know, you read something, you see something on Russian television. Do you believe it? You see something on Fox News. You believe it? You know, we're trying to rank different news sources. We're struggling to know what is truth, what is true, and that's very difficult. We find out. And so I'm not convinced that the semantic web is necessarily the way to make progress on the web. But, you know, there are people who are very passionate about it, and maybe they're right. So we'll just have to wait and see how it unfolds.
Okay, thank you. Now, Professor Dilhi Babu, you have a question.
Yeah, Moshe, thanks for the talk because I cannot unmute because of some problem here. Okay, so I saw that your talk is really good because of because I'm working in logic, you know that. So my question is precisely for machine learning part of, okay? The last questions, same thing, because of I can see that in machine learning currently people are working on predictions, okay? Most on that working on deep learning with predictions. Do you think that any like logic, because the description logic is not applicable, but do you think that deep learning concept can be do it in something logic perceptions? Any idea?
Say that again.
For deep learning.
So you know, deep learning has been enormously successful. I mean, really, if you just look at the machine learning today and the way it was just about a decade ago, it's just like we are in a different world. There's been just a amazing difference. Okay.
Yes. Yeah.
And however, people are feeling that there is a problem with deep learning per se, which is okay. It's essentially a deep learning is a big blob. You give it something and it says, yes, it's a cat, it's a dog. Okay. And as long as we are trying to distinguish between cats and a dog, okay, maybe it's good enough. But now I'm trying to tell you, okay, this is cancer, this is not cancer. And this will have serious consequences for medical consequences. So we would like to know more than just yes, no. So just to give you an example, we all have to write reviews for people, for papers. Imagine that you get to review a paper and you write back to the editor who asked you to review the paper, I recommend rejection. This is it, one line, I recommend rejection. The editor will look at this recommendation and he said, this is useless. You just give me, you know, I know you're a famous scientist, but this is useless, so give me an explanation. So this gave rise to what people want today is to explainable AI. And we want machine learning to explain the reasoning. But if the reasoning is just this neuron fired and therefore this neuron fired, that's not an explanation, satisfactory explanation. Okay? I mean, just like it's going to be my writing a letter, rejected paper because I don't like it, not an explanation. And so people are now starting to talk more and more about neurosymbolic reasoning. And we need to have some symbolic language because human beings talk in a symbolic language, okay? And we want reasoning that makes sense to us in some language. And so there is a sense now that just going by deep learning by itself is reached, I mean, major accomplishments, but we need to go to the next level. And the next level to me is combining symbolic and neural reasoning. And, you know, I have a whole talk that just goes into that direction. What do we have to do for logic to be able to integrate it with neural reasoning?
Okay, thank you very much. There are also personal questions from Mikhail Bakhterev, as I understand. The question is the following: and what do you think about the role of intuitionistic logic, type theories, and type free truth theories? Do you see the question here?
It's in the chat.
Yeah.
So, I mean, you know, if you look at, I'll tell you a kind of funny story. When I was a postdoc, I was a postdoc at Stanford, and I said, okay, I need to learn more logic. So I took 2 classes in model theory, a basic class and advanced class, and it influenced me very much. Then I said, I need to take a class in proof theory, because that's the other leg of mathematical logic is proof theory. And the professor was a famous proof theorist, but he spoke very softly. He spoke like this, very, very softly. And it was a small room, and I could barely hear him. And after like 15 minutes of struggling just to hear him, I said, Professor, could you please speak a bit louder? And he said, I will try. I will try. And I just could not continue because all my effort in the class was just to listen, to understand what am I hearing, not what am I understanding. So I admit that my background in proof theory is weak, but there are people who have studied proof theory, and for programming languages, for example, if you want to understand the semantics of programming languages, what does the program mean? Then you need to get into types, and you need a whole bunch of other type of, and we know there is a very tight connection between types and proof. There is something called proposition as types. So it's a rich area, and you need to bring someone else to give this talk. It just I'm not the person who's qualified to give such a talk.
Thank you very much, Professor Vardi, for a very interesting and useful for all of us talk. And let us at last to applaud for thanking Professor Vardi. And we hope very much that there will be favorable times will become, and you will attend our cousin Federal University, our Scientific and Educational Mathematical Center, and we will listen you personally. Thank you very much.
Amen, amen. I look forward to that very much.
Good, thanks. So
Okay.
we can finish now.
До свидания, до свидания.
До свидания.